Hello. Welcome to my channel. In this video we will go through the problem 7.5 of chapter number 7, electrodynamics. Okay, and the book we are following is Introduction to Electrodynamics by David J. Griffiths. Before starting the video, I will request you to subscribe my channel and please press the bell icon so you won't miss any of the upcoming videos. And the link of the playlist of all the problems of chapter 7 is given in the description. Okay, so you can visit the playlist from the description box. Okay, now let's head toward the problem 5. This problems we have given with some basic information, which is we have a battery of EMF which is E and internal resistance of R. Internal resistance R, okay, and is hooked up to variable load resistance R, and this resistance is variable, okay, and it is R. And if you want to deliver the maximum possible power to the load, what resistance R should you choose? Okay, you cannot change E and R, of course. Okay, so we cannot change these two quantities, internal resistance and EMF of the battery. Okay, so the required thing is we have to find is the maximum power delivered, the maximum power delivered on which resistance. Okay, we have to find this solution. So as we know that P equals to I square R, which is Joule's law. Okay, we miss I. Okay, so we don't know what current flows here. Okay, so we will find I from KVL. Okay, it is Kirchhoff voltage law, which says that the terminal voltage of a battery, here we can say if we have this battery, the terminal voltage, which is V, okay, it will be equals to EMF minus current flowing in the circuit multiplied by internal resistance, which is R. So here V equals to IR and EMF is E. Okay, so we can say that IR equals to EMF minus I into internal resistance R. So when we will add this term on both sides, we will get IR plus internal resistance multiplied by current equals to EMF of the battery. Okay, IR plus I multiplied by internal resistance is equal to EMF, and as we know that the current in the circuit is same, so this is common and we will take I common. This is R plus R equals to EMF, and we will divide R plus R on both sides, so we will get I equals to EMF divided by capital R plus small r, which is internal resistance. Okay, this is the current flowing in the circuit. Let's say it is equation 2. Okay, now we will put equation 2 back in 1, so we get that the power delivered is equal to, which is equation 1 was P is equal to I square R, so it will be like EMF square divided by R plus R square, and this will be R. So this is the power delivered to the resistor R. Okay, this is the power delivered to the external resistance. Okay, so now we have to find when will maximum power delivered, okay, delivered to R. Okay, so to find this, okay, from maximum power transfer theorem, we can obtain that R should be equals to R, but we have to prove this. Okay, the maximum power delivered to the external resistance, external load, is when the internal resistance is equal to external resistance. So we have to prove this. Okay, we got that P is equal to EMF square divided by R plus R whole square, and this is R. Okay, now to get the maximum and minimum of something, we take the derivative and put it equals to 0. Okay, because derivative is always equal on the peaks. Okay, now for example, this is a slope, and on this peak and on this peak the derivative is 0. This is minimum and this is maximum, so we will take the maximum. So we differentiate it with respect to R. Okay, so dp divided by dr, sorry, this is p, this is p, and this will be like EMF square divided by R plus R whole square, and this is R. Okay, so we will differentiate it in the next slide, so we make sure that we got an extra space. Okay, now to find this derivative we will use the quotient rule, which is given here. So if we face this problem like the derivative of m by n, okay, with respect to some function x, so we will say that first of all we will take the denominator, okay, and then we take the derivative of numerator minus numerator, and we take the derivative of denominator divided by denominator square. Okay, so by using this rule, and we will also make this equal to 0, because in order to get the maximum or minimum of a derivative we will put it 0, because always the maximum or minimum of a function give the derivative 0. Okay, on the top the derivative is always 0. Okay, so the derivative of dp by dr is equal to r plus r whole square, which is denominator here. Okay, and by taking the derivative of numerator, e square is constant, we will get the derivative dr divided by dr minus, and now we will take the numerator without differentiating, and then differentiate the denominator, which is r plus r square. So, and this is r plus r squared divided by dr, and we differentiate sorry, and we write it. Okay, now this will be equals to, this will goes to 1, and this will be like r plus r whole square, and this is EMF square minus, and this will also be 2 into r plus r. Okay, and then it will give us 1 plus 0. Okay, divided by r plus r whole square. So okay, this is already squared, so it will become power 4. Okay, this was a mistake. So, and here we missed something, e square. Okay, now let's see, this will become dp divided by dr, sorry, this is equal to r plus r whole square and EMF square minus r plus r whole square and EMF square minus EMF square into 2r into r plus r. Okay, this equals to 0, and here we have r plus r to the power 4. Now this will multiply here and we get this 0, so we get left with r plus r whole squared, and this is EMF square, and this will become equals to EMF square into 2r into r plus r. Okay, this is the main thing we get here, so this will cancel out. Okay, now opening this formula, which is a plus b whole square, so this will become r square plus 2 r and r, which is equal to if we multiply this inside, this will get 2r square plus 2r and r. Okay, you can see that here we have plus 2 r, and here also this will cancel out each other. Okay, and we only left with r square plus r squared is equal to 2r squared. Okay, now we will move this toward that side, so r squared 2r squared, okay, minus this r square equals to r square. Okay, now this will become r square equals to r square, and by taking the root on both sides, this and this will cancel, so r equals to r. Now here we have proved that when r equals to r, which is the maximum power theorem, okay, and we have proved it here. So when r is r, the maximum power delivered. So if you found this video helpful, please subscribe to my channel, like the video and press the bell icon so that you won't miss any of the upcoming problems. Please comment if you have any question and if you have any suggestion. Thank you very much. Be my support.